Welcome to Lecture 3 of Electrical Engineering 525. The first problem we will look at in this lecture is problem 2.5-3, which says that an antenna has a far-field pattern which is independent of phi, but varies with theta as follows. And you can see here that f is given here as a function of theta. And it has different values for different ranges of theta. And we're asked to find the directivity and also the directivity in the direction theta equals 90 degrees. So we can begin by recalling from page 53 that the directivity is given by this formula, where omega sub A, remember, is called the beam solid angle, and it is defined on page 52 as follows. This is integral over the unit sphere of f of theta and phi magnitude squared. And just a quick note, if you look at example 2-3 on page 54, although the answer given there is correct, in the example itself, it incorrectly has this formula as with the 2 here. This exponent of 2 is missing, so that's just a minor mistake in the textbook. This is the correct formula right here. You should have the integrand is the magnitude of f and theta phi squared. So let's go ahead and compute d as requested. We have 4 pi divided by the beam solid angle, and here we substitute that formula for the beam solid angle. And remember that for the unit sphere, using spherical coordinates, d omega will just become sine theta d phi d theta, and phi varies from 0 to 2 pi, theta varies from 0 to pi. Nothing in this problem varies with respect to phi, so we can separate the theta and phi integrations as we've shown here, and this integral of d phi from 0 to 2 pi just gives 2 pi. And so this quickly simplifies to this expression: 2 divided by the integral from 0 to pi of f of theta magnitude squared sine theta d theta. Now the only challenge here is that we need to break up this integral into different parts, because this expression magnitude of f of theta squared has different expressions or different values over different ranges of theta. Recalling up here, when we square this, then it'll be equal to 1 from 0 degrees to 30 degrees, and then it will be equal to 0.5 squared from 60 degrees to 120 degrees, and 0.707. This is square root of 2 over 2, or 1, or let's say 1 over square root of 2. So when we square that, we'll get 1/2 in this region, and then 0 in these regions. So we just need to remember that as we write the integrals. And here that's done, and we have changed all the angles to radians. And you can see that f is being squared in each case, and then multiplied by sine theta d theta, and then integrated. And so we go ahead and do all of those integrals and evaluate them between the appropriate limits, and we end up getting d is equal to 4.435. And in dB, we will get 10 log of 4.435, or 6.47. So that's the desired answer for the directivity. And now for the directivity in the angle of theta, in the direction of theta equals 90 degrees. The formula to get that is d times f of 90 degrees magnitude squared. And that formula, by the way, is equation 2-145. And so we take the directivity 4.435, and we evaluate f of 90 degrees and square that. If you look at 90 degrees here, 90 degrees falls in this second category for theta between 60 and 120, and in that range f is equal to 0.5. So we come back down here and we will have 0.5, and remember it's supposed to be squared, so we get 1.109, and so the directivity in the direction theta equals 90 degrees is 1.109, or if we want it in dB, we take 10 times the log of 1.109, or 0.45 dB. So that finishes that first problem. Again, that was problem 2.5-3. The second problem we want to do for this lecture is 2.5-9. It says that an antenna has a directivity of 20 and a radiation efficiency of 90%. We want to compute the gain in dB. This is a very easy problem. From page 55, we have the formula that the gain is equal to the radiation efficiency times D. And so since the radiation efficiency is 90% and D is 20, the gain is 18. We want to compute the gain in dB, so we just take 10 log of 18 and we get 12.55 dB. So that's a very simple problem. Now we'll go to problem 2.8-1, where we will talk about polarization. And this problem states the following. It says that the instantaneous electric field components of an elliptically polarized wave are Ex equals E1 cosine of omega t minus beta z, and Ey equals E2 cosine of omega t minus beta z plus delta. Specify E1, E2, and delta for the following polarizations. Okay, now in all of this, we'll go ahead and assume that E1 and E2 are both greater than, let's say greater than or equal to 0. We won't consider the case of either one being negative. And the reason for that simply is that that could be taken care of by adjusting the arguments inside the trig functions. So we're not gonna do that. We'll just assume that E1 and E2 are both non-negative. So we want to consider the three cases. A is linear polarization with E1 and E2 both non-zero, and then B is right circular polarization, and C is left circular polarization. Now, so we do A first. Now, the reason we're specifying in A that E1 and E2 are both non-zero is that you can have linear polarization where one of those is equal to 0. In fact, if E1, remember E1 is the magnitude here, or the amplitude of Ex. So if E1 is equal to 0, we would have vertical polarization. On the other hand, if E2, and I should say if E1 were equal to 0 and E2 was not equal to 0. If both were equal to 0, then we don't have any polarization at all. That's just no electric field. So we wouldn't have both equal to 0. But if we had E1 equal to 0 and E2 not equal to 0, that would be vertical polarization, because the field would oscillate back and forth along the y-axis. On the other hand, if we had E2 equal to 0 and E1 not equal to 0, then we would have horizontal polarization because the field would oscillate back and forth along the x direction. But in this case, we have E1 and E2 both non-zero, and so we're going to have the electric field going back and forth along some line that is tilted with respect to the xy axis. And of course, the equation then of a line that's tilted would be EY is equal to alpha EX. So we have, remember, EY is E2 cosine omega t minus beta z plus delta, and EX is E1 cosine of omega t minus beta z. Somehow the alpha got left out of this, so I'll put the alpha in here. So we have alpha, and here is alpha. And remember that alpha is a constant. In fact, let me emphasize, alpha is a real constant. So, on the left-hand side now, we will use the formula for the cosine of a sum to rewrite this term cosine of omega t minus beta z plus delta. And that will become cosine omega t minus beta z cosine delta minus sine omega t minus beta z sine delta. And on the right-hand side, we're just left still with alpha E1 cosine of omega t minus beta z. Now, this is these two expressions, the left-hand side and the right-hand side, are equal to each other for all times t. And for that to be true, we must have that sine delta, this term involving the sine omega t minus beta z on the left-hand side, it must go away. So that must mean that sine delta is equal to 0. And of course, that will happen when delta is equal to n pi, where n is any integer. And of course, what we're left with then is E2 cosine of omega t minus beta z. Remember, if delta is equal to n pi, then we would have cosine of n pi here, which would be negative 1 to the n. So we would really have then E2 times negative 1 to the nth power is equal to alpha E1. That would be the relationship between E1 and E2 and alpha, where again, remember, delta is equal to n pi. Now, if we've already said that E1 and E2 are both positive, so that would put some restrictions on your possible choices of alpha and n, which would also, since n is related to delta, that would put certain restrictions on delta as well. Now for parts B and C, where we're dealing with circular polarization, for circular polarization, the absolute value of the maximum value of Ex must be equal to the absolute value of the maximum value of Ey. So these two amplitudes, E1 and E2, must be equal to each other. So here we have E1 equals E2, and we don't want the case where the electric field is 0, so both of these are non-zero. And so now the question is, what can we say about delta In this case, where we want right circular polarization. Well, the easiest way to do this kind of problem is to begin by expressing both Ex and Ey in terms of the same trigonometric function. Now, in the case given here in this lecture, that's already done. In other words, both Ex and Ey are being expressed in terms of the cosine. But if, for instance, Ey were written in terms of sine, we should simply use the fact that the sine of alpha is equal to the cosine of alpha minus pi over 2 to rewrite Ey in terms of cosine, since that is the way Ex is given. So it's easy to make the adjustments so that both Ex and Ey are written in terms of the same trig function, and that is the first thing you should do in this kind of problem. Now that we have both Ex and Ey written in terms of the same trig function, we distinguish between right circular polarization and left circular polarization as follows. First, point the thumb of your right hand in the direction of travel of the wave. In this case, that's the direction of travel is the plus c direction. Then note as time progresses whether or not E rotates in the direction in which the other fingers of your right hand curl as you make a fist. If so, you have right circular polarization. If not, you have left circular polarization. It's just that simple. So in this case of a wave traveling in the plus c direction, Ey will lag Ex by pi over 2 for right circular polarization and lead Ex by pi over 2 for left circular polarization. Once we observe that, then we can easily complete the problem. So for right circular polarization, we have, remember, Ey lags, so the phase of Ey, which is omega t minus beta z plus delta, minus the phase of Ex, which is omega t minus beta z, is equal to minus pi over 2 plus 2 and pi. So we get delta once we go ahead and simplify this, omega t, that'll go away, minus beta z minus the negative beta z, that goes away. So we have delta is equal to minus pi over 2 plus 2 and pi. And on the other hand, for left circular polarization, we'll get delta is equal to positive pi over 2 plus 2 and pi. So if you do this kind of problem in this way, it's really straightforward. So that's the way I suggest doing these problems with circular polarization. And that concludes lecture 3. So good luck.